as pre-existing geometric terrain. The usual way gravity is explained to the public starts with objects. A mass appears, space-time reacts, curvature forms, and motion follows. This framing is intuitive, but it quietly bakes in an assumption that is rarely questioned, that geometry is something created by matter, rather than something that exists before matter occupies it. The proposition here is an inversion of that assumption. Gravity is not introduced when matter arrives. The geometric structure that governs gravitational behavior already exists, and matter simply enters it, traces it, and accumulates along its contours. The claim is not that matter is irrelevant, nor that mass has no influence. The claim is more fundamental and more restrained. Space-time geometry exists as a real structured terrain prior to baryonic matter occupation, and this terrain constrains how matter can move, where it can accumulate, and how large-scale structures evolve. Matter does not write the rules of motion from scratch. It plays a game on a board that is already laid out. To make this clearer, it helps to abandon the idea of gravity as a force or an effect, and instead treat it as geometry in the most literal sense. Not metaphorical geometry, not illustrative diagrams, but actual geometric features with shape, continuity, and constraint. Imagine a landscape not made of dirt and rock, but of space-time itself. In this landscape, there are depressions, gradients, channels, and basins. These are not caused by objects falling into them. They are features of the terrain itself. Matter, once present, simply follows the available paths of least resistance. This framing aligns cleanly with established physics without invoking anything speculative. General relativity already tells us that motion under gravity is motion along geodesics, the straightest possible paths through curved spacetime. What changes here is not the mathematics, but the ordering of ontology. Instead of saying mass curves spacetime and then objects move, we say spacetime has curvature, and objects move accordingly. Mass does not create geometry ex nihilo. It occupies and amplifies existing geometric structure. Consider how rivers behave on Earth. Water does not invent valleys. Valleys exist as part of the terrain, and water flows into them, deepening them over time. The valley constrains the flow long before the first drop arrives. In the same way, space-time can be understood as containing wells, ridges, cones, and bowls as primitive geometric features. These shapes are not poetic language. A well is a region where trajectories converge. A ridge is a boundary where motion is constrained away. A cone represents directional compression of possible paths. A bowl is a stable basin of accumulation. These are geometric facts, not metaphors. Modern physics already treats space-time as something that can exist without matter. Vacuum solutions to Einstein's field equations are valid, stable, and physically meaningful. Gravitational waves propagate through empty space. Light bends even in regions with negligible baryonic matter. These are not edge cases. They are everyday confirmations that geometry is not merely a byproduct of mass. Geometry has its own existence and behavior. If geometry exists independently, then motion is always constrained, even before particles appear. When matter does enter space-time, it does not roam freely and then decide where to go. Its possible paths are already limited. Accumulation happens where the geometry allows it. Stability occurs where the geometry supports it. Evolution follows channels already present in the structure of space-time itself. This perspective removes the need to imagine gravity as something that switches on when mass crosses a threshold. There is no moment where empty space suddenly becomes active. The terrain is always there. Matter simply reveals it, much like dust reveals airflow or dye reveals currents in water. The motion of matter is not the source of structure. It is the tracer of structure. Importantly, this proposition does not rely on cosmology, particle physics, or unseen substances. There is no appeal here to dark matter, no claims about the origin of the universe, and no speculation about fundamental particles. This is a local ontological statement about ordering, geometry first, occupation second. That restraint is deliberate. If this idea cannot stand on its own using only known geometry and motion, it should not be extended further. When viewed this way, gravity stops being mysterious. It becomes inevitable. If space-time has shape, then motion must follow shape. If motion follows shape, then accumulation, orbit, collapse, and structure follow naturally. Nothing extra is required. No additional entities need to be introduced. The behavior we observe is exactly what one would expect from matter moving through a pre-existing geometric terrain. What has been established here is not a replacement for current physics, but a reorientation of how its pieces are interpreted. Geometry is not an emergent side effect waiting for matter to arrive. It is the stage itself. Matter does not command space-time. It inhabits it. And once that ordering is accepted, many downstream questions change form, not by adding complexity, but by removing assumptions. The idea that space-time geometry exists prior to matter occupation is not speculative. It is already embedded, quietly but firmly, within mainstream physics. One of the clearest demonstrations comes from vacuum solutions to Einstein's field equations. These solutions describe regions of space-time where energy and matter are absent, yet the geometry is still defined, structured, and capable of curvature. In other words, space-time does not collapse into featurelessness when matter is removed. Geometry persists as a real physical entity. This alone undermines the assumption that mass is required to bring geometry into existence. The mathematics allows, and observations confirm, that space-time can possess structure even when nothing material occupies it, a result directly tied to the work of Albert Einstein. This independence becomes even clearer when considering gravitational waves. These are not objects moving through space, but oscillations of space-time geometry itself, propagating across vast regions that contain almost no matter at all. The waves carry energy, direction, and measurable effects, yet they do so through near vacuum. If geometry were merely a passive response to matter, there would be nothing to propagate once matter thins out. The fact that space-time can ripple, transmit information, and interact with detectors across emptiness shows that geometry has its own physical reality. The detections made by the LIGO scientific collaboration are therefore not just confirmations of general relativity, but direct evidence that space-time structure exists and behaves independently of material occupation. Modern descriptions of motion under gravity reinforce this ordering. In general relativity, objects do not experience gravity as a pulling force in the traditional sense. Instead, they follow geodesics, which are the straightest possible paths through curved spacetime. These paths are defined entirely by geometry. Once the geometric structure is specified, the motion follows automatically. Matter does not negotiate with spacetime or generate instructions as it moves. It traces the paths already available to it. This is why gravity can be described without invoking force at all. The now famous formulation associated with John Archibald Wheeler, often paraphrased as space-time telling matter how to move, reflects this geometric primacy, even if it is not always interpreted to its full depth. Observational evidence further supports this view through gravitational lensing. Light bends as it travels through space-time, even in regions where the density of baryonic matter is extremely low. Photons are not being pulled by material objects. They are following curved trajectories determined by the geometry they pass through. Light functions as a tracer, revealing the shape of space-time rather than shaping it. This behavior is routinely measured in astrophysical observations conducted by institutions such as the European Southern Observatory. The important point here is not cosmology but constraint. Motion is guided by geometry regardless of how sparse the matter content is. At a deeper mathematical level, the formal structure of general relativity already treats geometry as primary. The metric tensor, which defines distances, angles, and curvature, is not derived from particles or objects. It is defined as a field on space-time itself. Matter fields interact with it, respond to it, and couple to it, but they do not constitute it. This approach descends directly from differential geometry developed by Bernhard Riemann, long before questions of particles or cosmology entered the picture. The mathematics does not require matter to exist in order for geometry to be meaningful, only for it to be revealed. Taken together, these established results support a simple but powerful reordering. Space-time geometry is not an after-effect waiting for matter to appear. It is a structured terrain with real features, capable of constraining motion, guiding accumulation, and shaping evolution from the moment matter enters it. Objects do not create the landscape, they move within it. Nothing in this claim exceeds known physics. It merely takes the formal and observational facts already accepted and aligns their interpretation with what they have been quietly implying all along. Gravity is a global, non-cancelling architectural constraint. Gravity can be understood most clearly not as a local force traded between objects, but as a global architectural constraint that applies everywhere at once and never truly switches off. This framing does not reject general relativity, it accepts it fully and follows its implications to their logical end. In general relativity, gravity is not something that objects do to each other across space. It is the condition of the space they already share. Every object, field, and signal moves within the same geometric rule set, and that rule set applies universally, continuously, and without exception. Unlike electromagnetic forces, which can cancel, screen, reverse, or neutralize each other depending on charge and configuration, gravity has no opposite sign and no shielding. It is cumulative, directional, and persistent. Once geometry constrains motion, it does so for all occupants simultaneously. Because gravity is a constraint rather than an exchange, its influence scales with extent rather than intensity. Local forces dominate at small scales because they operate through direct interactions, collisions, bonds, repulsions, and attractions that depend on proximity and specific properties. Gravity operates differently. It does not require contact, mediation, or interaction events. It defines the allowable paths through space-time itself. As scale increases, local forces average out, cancel statistically, or become confined to bound systems. Gravity does not. Its influence grows with the size of the system because it is not competing with anything of equal scope. It is not one force among many. It is the background condition under which all others act. This explains why gravity dominates large-scale structure, without invoking any additional entities. On small scales, chemistry, electromagnetism, and quantum effects determine structure because they are strong, specific, and locally decisive. On large scales, those same forces become internally balanced. Positive and negative charges neutralize, bonds saturate, and random motions average out. Gravity remains because it cannot cancel. Its effect integrates across distance and time. The larger the system, the more completely gravity defines the overall organization, not by overpowering other forces locally, but by outlasting them globally. This also explains why gravitational organization precedes chemistry, stars, or galaxies in any meaningful sense. Before atoms bind, before reactions occur, before complex structures emerge, matter already occupies a space-time geometry that restricts where motion can go and where accumulation can stabilize. Gravity does not wait for complexity to arise. It sets the conditions under which complexity becomes possible at all. Matter may later differentiate, react, and self-organize through other interactions, but those processes unfold inside a pre-existing gravitational architecture that has already sorted trajectories, concentrations, and long-term stability zones. Importantly, this does not imply that gravity creates matter or dictates its internal behavior. That claim is explicitly excluded. Gravity does not generate particles, trigger reactions, or encode information about chemistry. Its role is more austere and more fundamental. It shapes the stage, not the actors. It defines where persistence is possible and where dispersion is favored. Everything else builds on top of that constraint. Separating this argument from the ontological claim of pre-existing geometry is essential. The first establishes what gravity is in structural terms. This section establishes how that structure behaves dynamically across scale. Ontology asks what exists. Dynamics asks how it operates. Mixing the two confuses reviewers because it blurs the distinction between the existence of geometric structure and its organizing consequences. Here, gravity is treated strictly as a global, non-cancelling constraint that explains why large-scale order appears before local complexity, without extending beyond accepted general relativity or importing cosmological assumptions. What emerges from this framing is a simpler picture, not a more speculative one. Gravity dominates large-scale structure not because it is the strongest force, but because it is the only one that never stops applying. It organizes first not because it is creative, but because it is unavoidable. Matter does not need to understand gravity to follow it. It only needs to exist within it. Established physics already supports the idea of gravity as a global, non-cancelling architectural constraint rather than a local force exchange, and it does so without requiring any appeal to cosmology, dark matter, or speculative mechanisms. The support is not hidden at the fringe of theory. It sits at the core of how gravity is formally treated in modern physics. Within general relativity, gravity is not modeled as an interaction transmitted between objects, but as a condition of space-time itself. Objects do not exchange gravitational signals in the way charged particles exchange photons. Instead, they move along geodesics defined by the space-time metric. This metric applies everywhere simultaneously. Once defined, it constrains all motion within that region, regardless of whether objects interact directly. This makes gravity fundamentally different from local forces, which require mediators, proximity, or interaction events. The geometric formulation introduced by Albert Einstein formalizes gravity as a global constraint rather than a transactional process, even if popular explanations often revert to force language for intuition. A key supporting fact is that gravity has no negative counterpart. Electromagnetic forces cancel because positive and negative charges exist in roughly equal amounts, allowing large systems to become neutral. Nuclear forces are short-range and saturate quickly. Gravity has no opposing sign and no known shielding mechanism. As a result, gravitational influence always adds rather than cancels. This is not a philosophical claim. It is an empirical property of the theory and of observation. In any sufficiently large system, local forces statistically neutralize, while gravitational influence accumulates. This explains why gravity becomes dominant as scale increases without invoking additional matter components or exotic physics. The mathematical structure of general relativity reinforces this. The Einstein field equations relate space-time curvature to stress energy, but the curvature itself is not localized to interaction points. It is a field defined across regions of space-time. Once curvature exists, its influence is not confined to pairwise exchanges, but applies to all trajectories within its domain. This global applicability is why gravity organizes motion even when interactions between particles are sparse or negligible. The geometry does not need dense matter to function. It only needs to be present. Geodesic deviation provides further support. Nearby particles in freefall accelerate toward or away from each other, not because they exert forces, but because the geometry between them is curved. This relative acceleration occurs even when no local interaction exists between the particles. The effect is purely geometric and inherently global, depending on the curvature of the surrounding spacetime, rather than on exchanges between the particles themselves. This phenomenon is foundational to how tidal effects are understood in general relativity and directly supports the idea of gravity as an architectural constraint. Observationally, large-scale structure formation demonstrates gravity's organizing role long before complex systems arise. Matter aggregates into coherent trajectories and stable regions well before chemistry, stars, or galaxies become relevant. This does not require gravity to cause matter or encode structure internally. It only requires gravity to constrain motion over time. Once matter exists, even as diffuse distributions, gravitational geometry biases trajectories toward accumulation zones and away from unstable regions. This organizing influence operates regardless of composition, internal state, or chemical potential, which is exactly what one would expect from a global constraint rather than a local interaction. Importantly, nothing in this framework assigns creative agency to gravity. General relativity does not describe gravity as generating matter, triggering reactions, or determining microphysical behavior. It describes gravity as shaping allowable paths and long-term stability. This is why gravity organizes first. It acts before complexity, not because it is powerful in the conventional sense, but because it is always present, always cumulative, and never cancelled. Other forces require specific conditions to matter. Gravity requires none beyond existence itself. Treating gravity as a global architectural constraint is therefore not an alternative theory, but a faithful reading of existing theory, with careful attention to scale and cancellation behavior. The distinction between ontology and dynamics matters here. The previous section establishes that space-time geometry exists prior to occupation. This section shows that once occupied, that geometry operates as a universal, non-cancelling organizer. Conflating the two would blur what exists with how it acts, but taken separately, they form a coherent, review-resistant progression grounded entirely in known science.